So in this video, we're going to think a little bit about what happens in nerve cells when we have what's called an action potential. So that's a nerve impulse. And we're going to think about what the cell biology of that is underlying it. Okay, so let's think about a couple of definitions first. Okay, so potential is a word that comes from physics. So it means the potential to do work. And what that actually means is it refers to a separation of charge. So if we have in a biological system, if we have a membrane and we have one side of it is more positive and one side of it is more negative, that difference in charge we refer to as a membrane potential, and that has the potential to do biochemical work for us. Okay, so we have a phenomenon called potential. Okay, and then you might have seen a graph like this before in describing the action potential. So we express action potentials in terms of millivolts, and I'll explain where that comes from in a second. So we might have a graph that looks something like this. Then we start, then we have a very rapid increase, a decrease, and then it restores something like that. So we might get to plus 30 millivolts up there, for example. Okay, and there's an important words in, this is called electrophysiology. So if we're thinking about potentials, so anything where we're going more positive, we call depolarization. So there's to become more positive. Okay, so we're going from negative things to positive things, and in the other direction, then we would repolarize. Which would be to become more negative. Okay, so we have this characteristic shape of the voltages across the cell membrane. So what we're going to do is to try and understand that, where those voltages come from and how that relates to the transporters at the membrane. Okay, so let's start off with the first phase of this is the sort of flat line, the baseline status we call the resting potential. So this is the sort of baseline. Doesn't mean that the cell is at rest. The cell is actually doing quite a lot, but we call this the resting potential. This is before any sort of stimulus has come across. Okay, so let's have a think about that one first. So what is happening with a resting potential, and what does it mean to say that the membrane is at minus 70 millivolts? Okay, well here's the plasma membrane. Okay, so this is the outside of the cell, this is the inside or the cytosol. Okay, so we have a membrane, and as you remember, membranes, because they're hydrophobic, ions can't just move across the membrane, they have to move through a membrane transporter. Okay, and the transporter that is most important in the resting state is a protein called the sodium potassium ATPase. Okay, so the sodium potassium ATPase. And what this enzyme does is it uses the energy from ATP. So it hydrolyzes ATP to become ADP. And as we know, that releases energy. And it uses the energy to move some ions around. So what it does is it pumps out 3 sodiums and it moves in 2 potassiums. Okay, sodium is quite toxic in the cell, so this enzyme or this transporter is pushing the sodium out of the cell. So that means that we end up with a high concentration of sodium on the outside, and we have a relatively low concentration of sodium on the inside. Okay, but what it does, when it pumps out, it pumps 3 sodiums out and brings 2 potassiums in. So that means that overall we've got an imbalance of charge. So more positive stuff has left than has come in. So overall we get a difference in charge across the membrane. So it's more positive outside than it is inside. There's an imbalance in the ion movement. Excuse me. So that difference across the membrane, that difference in voltage, is what we call the resting potential. Okay, so that really refers to that charge separation over there. So because we've got the sodium potassium ATPase, that primary transporter is pumping sodium out and only letting a smaller amount of potassium back in. So we've got a resting potential across the membrane, and if we express that as a millivolt, if we measure that, then that's about minus 70 millivolts. Okay, so that difference in charge, the cell is spending energy to do it. It's not happening passively. This is an active process. The cell is spending energy to keep its resting potential down to about minus 70 millivolts. So that's what the resting potential is. So if the neuron is not stimulated, that enzyme will just keep going. There will be a bit of leak current, so it kind of stabilises out. But overall, that's what the main enzyme is doing, is to make sure that we've got minus 70 millivolts, so we're more positive on the outside than the inside. Okay. So let's now start to think about a stimulus happening. So the stimulus that we're going to think about is a pain stimulus caused by heat. Okay, so we've got a biological event happens. We've got pain, which we perceived in this case as heat, and this is perceived by a particular protein which is called TRPV, is the heat receptor. Okay, so what happens with our pain receptor? So we've got another protein here. Okay, so when this protein perceives a stimulus, so when it receives heat, so let's say you've touched a pan or something that's a bit hot. What that pain receptor does is to basically, it's an ion channel and it opens slightly. Okay, so it opens slightly. And when it does so, it's going to allow a couple of different ions through. So it allows 2 different ions through mainly. It allows sodium and calcium through. Okay, so here's our pain receptor protein. So remember that we've got high sodium concentration on the outside. It's going to be favourable for sodium to come into the cell. Okay. So we're going to have sodium coming into the cell, and what that's going to do is to reduce the imbalance in charge a little bit. It's going to get, so rather than having, let's put, so 1, 2, 3, 4, 5, 6, 7 pluses is our minus 70 millivolts. Because we've got a little bit of positive coming in, we're going to shift to maybe 50 millivolts. Okay, so we're going to get to minus 50 millivolts. So that's gone a little bit more positive. So we've got an initial depolarization. Okay, so this is what's happening here. Is we start to make the membrane a little bit more positive. Okay. And that starts slowly to start with, but then what happens is once we reach a particular threshold, which is round about minus 55, is another channel gets going. So we also have in the membrane, we have some sodium specific channels. Colour that in like that. Okay, so this is a sodium channel, and it is voltage gated. So that means it's regulated by the charge on the membrane. So when this protein is at minus 70 millivolts, it's closed. Okay, so it's closed at minus 70. It's closed during the resting phase. But when we start to shift the membrane just a little bit because of this pain receptor. What then happens is the protein opens. So there's actually a physical sort of little ball and chain bit of the protein that swings away. When that happens, that then opens the protein. So this might be at minus 50 millivolts. It's open. And when it's open, we have a big influx, very rapid influx of sodium. Okay, so this heat receptor only let a little bit of sodium out, but this protein allows lots and lots of sodium in very, very quickly. So we get a big depolarization. Okay, so that's what is happening in this part of the graph here. So we've got depolarization phase, and that is all to do with a large influx of sodium coming in, and there's so much sodium coming in that the membrane potential reverses. So it used to be positive on the outside, now it's positive on the inside relative to the out. Okay, so it's so much positive from the sodium that we actually flip the membrane potential, so it's now more positive inside. Okay. So we've had a massive influx of sodium, we've depolarized the membrane, but we need to start getting it back to its resting phase. Okay, so we have another protein, which is a potassium channel, which is also voltage gated. So that potassium channel, which I shall show here, that potassium channel is also going to be voltage gated, so it opens at positive voltages. So when we go really positive, that opens the potassium channel, so then we have a mass efflux of potassium outside of the cell. Okay, so what we'll do is we'll start to rebalance the charge. So we're starting to get positive a charge on the outside of the membrane again. So this is this repolarization. In there is all about potassium. The depolarization was all about sodium. Okay, so then the potassium is going out, so we're going to start to restore that original charge balance there. Okay, and then we've kind of got this lag phase in there, or sort of undershoot. Okay, that is the time it takes for the whole system to restore to normal. Okay, so during that lag phase, we'll start to get the ATPase kicking back in again. These channels will start to close again. So the lag phase is the amount of time it takes for the whole system to kind of rebalance itself. Okay, so in our resting potential, it's all about the ATPase, chucking out sodium, bringing in potassium, and establishing a potential, so that takes up energy. We then have a stimulus. So here we've got pain receptor, so that starts to depolarize the membrane. So we start to have an influx of positive charge. That activates a voltage-gated channel, so we have a large influx of positive charge. So we've got a massive influx of positive charge, which we call the depolarization. So that's why the graph goes very spiky. When we go to the positive, that opens the potassium channels. So the potassium channels open, so all the potassium starts to leave. So we get a very rapid depolarization, and then the system takes a little while to reset itself to normal to re-establish this resting potential at minus 70 millivolts. So we've got a couple of different types of transporters in there. So we've got an active ATPase, we've got some sort of receptor ion channel, and then we've got voltage gated ion channels that only open or close at particular membrane voltages. So the system all over is voltage dependent, but ultimately it actually depends on this primary ATPase at the beginning to establish that resting potential.